So why the square root of -1? It wasn't Charles Steinmetz who came up with the idea of the square root of -1. In fact, this concept had already been developed by mathematicians centuries earlier. But what Steinmetz did do was offer one of the most approachable explanations of these so-called imaginary numbers. Let's dive straight into his engineering mathematics to see how he introduces these ideas to the layperson. He begins with the fundamentals of counting and measuring. From the operation of counting and measuring arose the art of figuring, arithmetic, algebra, and finally, more or less, the entire structure of mathematics. Steinmetz reminds us that for early humans, and even for every child, the first conceptions of numerical values were vague and crude. Many and few, big and little, large and small. Over time, we developed the ability to count, to understand numbers, and eventually to measure. Even today, measuring often relies on counting, steps, knots, and other repetitive markers. From counting, Steinmetz explains, came the simplest mathematical operation, addition. He gives a practical example. We may count a bunch of horses, 1, 2, 3, 4, 5. Then we count a second bunch, 1, 2, 3. Now put the second bunch together with the first one into one group and count them. That is, after counting the horses of the first bunch, we continue to count those of the second bunch, thus 1, 2, 3, 4, 5, 6, 7, 8. But this straightforward process of addition introduces something more complex when we try subtraction. Negative numbers as mathematical fictions. Steinmetz emphasizes a critical point. Even negative numbers are, in a sense, imaginary. He writes, we must therefore realize that the negative number and the negative unit, -1, is a mathematical fiction and not in universal agreement with experience, as the absolute number found in the operation of counting. In practical terms, negative numbers don't always correspond to physical reality. For example, 5 horses minus 7 horses equals -2 horses has no physical meaning. There exist no negative horses. At best, we could express the relation by saying 5 horses minus 7 horses is impossible. 2 horses are missing. He extends this to other physical quantities, like light. An illumination of 5-foot candles lowered by 7-foot candles is impossible. There cannot be a negative illumination of 2-foot candles. The limit is 0 illumination or darkness. Negative numbers, Steinmetz argues, are meaningful only in certain contexts. In all cases where there are 2 opposite directions, right and left on a line, north and south latitude, east and west longitude, future and past, assets and liabilities, there may be an application of the negative number. In other cases where there is only one kind or direction, counting horses, measuring illumination, there is no physical meaning that would be represented by a negative number. The leap to imaginary numbers. Steinmetz draws an important parallel. The way we once struggled to accept negative numbers is similar to how we view imaginary numbers. He writes, the negative number is not a physical but a mathematical conception, just as imaginary numbers are. The only difference is that we became familiar with negative numbers earlier, when we were less critical, and usually do not realize they are a mathematical conception and not a physical reality. This means that imaginary numbers like the square root of -1 are just as valid or imaginary as negative numbers depending on the context. Connecting to the history. The concept of the square root of -1, which we now call imaginary numbers, can be traced back to Rafael Bombelli, an Italian mathematician from the 16th century. Bombelli introduced the idea while working on solutions to cubic equations that sometimes involve taking the square root of a negative number. However, the foundations of imaginary numbers weren't fully accepted until later. Mathematicians like René Descartes, who coined the term imaginary but used it dismissively, and Leonhard Euler, who popularized the symbol I for squirt -1, helped formalize the concept. Eventually, Carl Friedrich Gauss provided a more rigorous framework, showing how imaginary and real numbers together form the complex number system. So, while Bombelli gets credit for introducing the idea, it took centuries of refinement and acceptance for imaginary numbers to become a cornerstone of mathematics and engineering. Steinmetz bridges this abstract history with practical applications, showing how complex numbers open up new dimensions for solving real-world problems in engineering. By extending mathematics into new directions, literally, Complex numbers become indispensable tools for analyzing systems involving rotation, oscillation, and alternating currents. He begins with the fundamentals of counting, addition, subtraction, and gradually moves into multiplication, division, and what he calls involution, or powers. Once these operations are introduced, he takes us to the idea of roots and square roots. Here's how he lays the groundwork. The square root of 4 has two values, +2 and -2. In evolution, we thus first strike the interesting feature that one and the same operation with the same numerical values gives several different results. This naturally leads to the next question. Since all the positive and negative numbers are used up as the square roots of positive numbers, the question arises, what is the square root of a negative number? For instance, the square root of -4 cannot be -2, as -2 squared gives +4, nor can it be +2. To answer this question, Steinmetz introduces a new concept, numbers beyond the ordinary positive and negative, which he calls quadrature numbers. The leap to imaginary numbers. Steinmetz explains that numbers are derived from experience, such as measuring distances along a line. He writes, "We get the same distance from a starting point twice, once toward the right and once toward the left. This led to the subdivision of numbers into positive and negative." He illustrates this with a number line where movement to the right represents positive numbers and movement to the left represents negative numbers. Then he asks us to consider what happens when we multiply by -1. Multiplication by -1 reverses the direction, turning it through 180 degrees. But what about rotation by just 90 degrees? This is where the square root of -1 comes into play. Steinmetz explains, if we multiply +2 by the square root of -1, we get a new quantity, +2 times the square root of -1. Multiplying again by the square root of -1, we get -2. Thus, multiplying a number twice by the square root of -1 gives a rotation of 180 degrees. Multiplying once means rotation by 90 degrees. This new kind of number represents directions that are not along the usual left-right axis. Instead, they point upward or downward. Steinmetz refers to these as quadrature numbers and writes, "Quadrature numbers represent direction not toward the right as the positive numbers, nor toward the left as the negative numbers, but upward or downward." Here, connecting quadrature numbers to the plane, Steinmetz shows how these quadrature numbers extend mathematics into two dimensions. By the addition of quadrature numbers, all points of the entire plane can now be represented as distances from chosen coordinate axes. For example, a point in the plane has a horizontal distance such as +3 and a vertical distance such as +2 times the square root of -1. This combination of horizontal and vertical distances is written as 3 + 2j. He emphasizes that this new kind of number, which combines ordinary numbers and quadrature numbers, is called a general number or a complex quantity. The quadrature number enormously extends the field of usefulness of algebra by providing a numerical representation of two-dimensional systems, such as the plane.